Yeah, good question. Yeah, so that is showing you what happens to the tendons when they are held down in the hold down apparatus. They're stacked against one another. So that section, and you can actually see on the side view, you've got the first hold down that's on the left. I don't know if that's on the screen or not. Let me see if I can show it on the screen. This one wasn't one, I guess, that was given to you as an example on the slides anyway. Yeah, there's actually a section cut shown on the side view. You've got on the very right side, you've got the little section cut shown, and the arrows are pointing to the left, and that's cut right through that hold down nomenclature. So yes, it's showing you the dimension from the form up to the center of the lowest strand is 2 inches, and then it's telling you that each of those strands is a half inch, and there's 4 more of them, and then that gets you to the top. That gets you to the topmost strand.
All right, that's the only question that came in.
Okay. I'll apologize ahead of time for my voice. I've started to lose my voice a bit. I've got some head congestion over the past couple of days, so if you're having trouble understanding me or hearing me, just let me know, and I'll try to speak more clearly. So you've kind of made it through the bulk of the information that we'll cover in this class. Today we'll just be finishing up by covering Chapter 8 and Chapter 9, and Chapter 8 is really all about, as the title on the screen there suggests, product control. But really, what we mean by product control, I'll kind of paraphrase it in another way. It's what steps and procedures and practices do we have in place to make sure that the things we produce, the things we cast, and then we sell out of our plants, to make sure those things meet the requirements of the project. So that's really what we're talking about. And so we'll start off by talking about dimensional tolerances. This is something that all of you, I'm sure, are familiar with, especially if you're involved in the quality control department in any way. If you are owner facing, if you are dealing with the client or the architect, you're having conversations about what are your tolerances and what tolerances are necessary for the project. So PCI has a set of tolerances, but there are instances where the project requirements may be more stringent than what PCI requires, so you need to be aware of that. Just a few things to keep in mind when you're thinking about dimensional tolerances. One of the things that you want to be mindful of and think about ahead of time is the type of form that you're going to be using. If you've got a steel rigid beam form that you're using over and over and over again to cast bulb tees or double tees or something for a parking garage, or bridge girders or something like that, there's less opportunity for that form to become warped out of shape, and for those tolerances not to be met. If you're casting a wall panel on a wooden deck with wooden side forms that have to be built every time, you're introducing, the opportunity for user error to be introduced. And so sometimes the nature of the project governs what you have to do, and so you don't have a lot of choice, but you at least need to understand that with certain types of form work, meeting these tolerances may or may not be a little more difficult for you. So be prepared for that. Just the second bullet there, this is just telling you, what does it mean if you see this, um, uh, these dimensions written out in this format on a set of drawings: 100 feet 0 inches plus or minus 1/2 inch tolerance. That's telling you, or whoever's doing the setup, that the overall length could be 99 feet 11 and 1/2 inch, all the way up to 100 feet 0 and 1/2 inches. As long as it's within that range, that very first dimension that's given there, that's what that's telling you. As long as it's within that range, then it's okay. As I mentioned, there are some published tolerances that PCI provides. There are separate quality manuals. There are also some tolerances given in the back of the MNL 116 and 117, and then 130. 130 being the GFRC manual. The products that are listed are not. There's not a comprehensive selection. It's products that are common to those types of plants. The tolerance manual MNL 135 is a more comprehensive list of the different products that you might come across. Um, there are some other resources out there for you, um, but all of the things that PCI requires are published in their manuals. So if you can't find it in the MNL 116, then go to the MNL 135, and there will be information in there that will tell you what should the tolerances be for this type of product. And I'll give you an example. I'll come back to this slide, but figure 8.1, this is what a page from the tolerance manual, or this actually may be from, this is an example of tolerances from PCI MNL 116. So this is the structural PCI manual. So if you go to the back of that book, this is what a given sheet will look like. It'll give you the defining views, so side view, top view, and a section view, or section, top, side, in order of the way you see them on the screen. And then it tells you using these letters which dimensions are what, and then it tells you on the right hand side of the page, dimension A, for instance, the length of the double T, you have a tolerance of plus or minus 1 inch. So these are the PCI tolerances. If the project, the owner or the project specs or the construction documents or whatever that is part of the contract document says, well, for this job, the tolerance for length is plus or minus half an inch, then that's what you have to meet. You have to meet the more stringent requirement. There are instances where you may want to adjust the tolerances to meet the specific needs of a project. One instance that we might use as an example would be panel flatness. I'll show you some pictures of this momentarily, but what we're talking about here is if you're producing wall panels, for instance, on a steel form that has the potential to be dented or warped from use, and that is the form finish that maybe it's going to get sandblasted or acid etched at a later date. The expectation would be that those panels are totally flat. That's not always realistic. There's going to be slight imperfections in the form that are going to be very difficult for you to see with the naked eye under most lighting conditions. But when you see those panels that have been cast on a form that has slight imperfections under a raking light, in other words, sunlight shining on it from the side, you're going to see shadows that start to appear that are going to make very plain and obvious the imperfections in the form. So the point in me saying that is just to tell you that that is something that exists. That's something that has caused problems on projects before, where an owner wasn't educated on, well, here's the types of forms we use, and there'll be certain times of day maybe where you might see this shadowing appear. And I'll show you these pictures. So this is a panel that was produced on a form that had some slight waviness to it. And if you were to look at the form, you'd never see it. And even looking at this panel in this lighting condition, you don't see it. But when you look at the panel in the right light, you can see how this is the same panel that you saw here. And this light amplifies the imperfections in the form. You see all these little dents that are showing up that are shadowed through on the cast piece, especially right around in here. And so you see that, and you can understand why an owner or an architect might be disappointed or reject a panel because they weren't educated on the things that can happen. So, there are requirements for floor flatness and levelness that may be in the specifications. Be sure you know what the specs say. If you maybe it was in the spec and you didn't know what it meant, and you produced a panel like that, and maybe that doesn't meet the requirements of the spec, so then it would be rejected in that way. So there may be some conversations that need to be had on the front end to either say, well, we can produce these panels to meet these requirements, but we're going to have to build different forms, and that'll be, different cost, or actually, we think we can produce them, and we don't think you understand what the requirements mean. So it's a conversation that needs to be had between the producer and the owner or architect. There are also things like differential camber that need to be monitored and controlled. Um, Typically, um, half are, or actually, that's talking about the next thing. So with differential camber, hopefully you guys know what I mean by that. When you have, let's use a double T for an example, and I'll show you this image just so you can get it in your mind. So you've got a double T here that's got some camber. And what we mean by camber is the dimension from the theoretical horizontal line, and it's the dimension from there up to what is the upward deflected shape. What's the dimension from there to the new displaced center of the bottom of that piece? And the reason this camber happens is because of the pre-stressing. So you've got this pre-stressed component. It's got some camber, and you take this double T out to the field and you set it, and then you put one right next to it that also has camber, but let's say the cambers between the two are different. Say the first one was 2 inches and this one's 1 inch. Well, now all of a sudden you've got a 1 inch bump. So every time a car drives through that parking garage, every time they drive over a double T, it's like a speed bump. So there's things you can do as a plant to ensure that the cambers not only meet the requirement listed here, but also that the differential camber from component to component meets the requirements of the project. So there's you can load those in storage. You can ensure that the double T's that are going to be placed next to each other in sequence in the field are stored for similar amounts of time, so that camber grows to the same age. So there's things you can do to control that differential camber. With dimensional tolerances, ideally, and I think specifically what we're talking about here is like wall panel widths or double T widths, things where accumulating error is something you should be concerned about. Ideally, if you're going to be out of tolerance, some of those are a little high and some of them are a little low. And ideally, you're still within that tolerance range, but some of them are a little higher on the spectrum in that range, and some are a little low. So say you were looking at this double T, and the width of this double T, B, the tolerance for the width is plus or minus 1/4 of an inch. So what this is saying, this bullet point is saying, is that ideally, if they're going to be not dead on the dimension, then ideally some of them are a little high and some are a little low. And the reason for that is you want that to sort of offset. You want those slight variations to offset one another, so that the overall accumulating error, when you set those double T's back to back to back to back, if they were all a 1/4 inch low and you had 30 of them, now all of a sudden you're what is that, 7.5? You're 7 inches too short. So you want to be mindful of this concept of accumulating error, and try to make sure that if you're going to be off, that you can kind of skew those in one way or another to get that accumulating error to equal 0. Okay, so another major thing to think about and to consider, and to make sure you're technicians and those people in production are trained properly on the use of the not only using the correct measuring equipment, but on the proper use of that equipment. You always want to use an appropriately or the appropriate length tape measure. If you're measuring a double T that's 115 feet long, or a bridge gird that's 115 feet long, don't use a 35-foot tape and have to measure every 35 feet. You're building in error. It'll be really difficult to measure that accurately. Use a tape measure that's longer than the piece is, so that you can do that. You can make that measurement in one measurement. For what we're doing, typically temperature adjustments are not significant enough that they represent any kind of measurement error that would register even for the tolerances that we're dealing with. But it's also something to keep in mind. Us as auditors, we do not use, like for our 100-foot tapes, we don't use vinyl 100-foot tapes because they can stretch. We use steel tapes for everything we do. Anytime you've got an unusual shape, there may be instances where you have to build a jig. If you've got a radiused panel, it can be difficult to measure that with a standard tape measure without help or without some kind of a jig to give you a surface to measure to. So know your project, know your components, and know how to use the tape measure appropriately. Know where to measure. Typically I'll try to glance at your shop drawings of different pieces that you've got in production before I go out to measure anything. Even if it's not the same job, I look at those drawings just to say, okay, well, they're typically giving, the overall length or the thickness in this way, or if it's a bulb tee or a bridge girder or something, they're giving the measurement, based on this part of the height. So I'll at least know, okay, well, that's where I need to try to measure so that I can compare that measurement to what they're actually providing on the shop ticket. Every now and then, I guess wrong, and I try to measure where I think it might be, and I get back and look at drawings, and it's not exactly the same. We're not really comparing apples to apples, and I have to go do it again. But there's things you can do. Make sure you understand how you typically display information on your plant drawings, so you know where to measure. There are some plants that will, instead of using like a string line stretched across the bottom of a component and then measure up to the bottom to measure camber. That's one way you can do it. Another way would be to use a surveying level and just take multiple shots along the length of that piece to then plot what the camber is. So either one of those are acceptable. There are some plants that make very complex, um, uh, technically difficult pieces. I'm thinking specifically of things like tunnel liners. There are other products that are equally as complex, where not only are they radiused, but they're also radiused and sort of twisted. So you've got sort of this two-way curvature going on that would be, I wouldn't even say basically impossible. It would be impossible to measure accurately with a regular tape measure. And so there's different ways I've seen that be calculated and measured. I've seen plants use, robotic total station surveying equipment and a small little prism that's designed to be placed in very specific parts of that piece, and they'll take multiple shots with that surveying equipment, and then it plots a surface that can then be compared to compare the actual to the required, and determine whether or not the tolerances are being met. The other difficulty that comes in with things like that is sometimes those tolerances, and actually in most instances that I'm aware of, those tolerances are much tighter than what PCI would even allow, sometimes to the hundredth or tenth of an inch. And so you have to be very, very accurate with your placing procedures and your form work and all of that. Otherwise, you spend a lot of time and effort and end up having to scrap a piece because it doesn't meet the tolerance requirements. So in addition to dimensional tolerances, there's things that should be controlled in the plant that have to do with the aesthetic or the appearance of products that you send out the door. Um, this is a very important point, 8.2.1, establishing acceptance criteria. This is true for really anything you do, but this is especially true for architectural precast. If you are producing panels that are intended to have a very specific finish, a very specific aesthetic, usually that's something that's been arrived at, um, as a team with you, the producer plant, along with the architect and owner, and you've decided on here's what these panels should be and should look like. And it is very important to make sure that there are practices in place, um, to ensure that a consistent aesthetic is produced throughout the duration of that project. So one person should have acceptance authority, because everybody's opinion is subjective. So even if you have two people who are very experienced and have, um, arguably, uh, e- equally adequate opinions about what is good and what is right, they're still going to have variations in what they think looks good, or what they think, how colors appear to them, or that kind of a thing. So if possible, when possible, it should be left to one person to be able to say yes or no, that meets the standard, or no, that doesn't meet the standard. You also want to produce as many, um, variations, potential variations in the aesthetic as possible, that are part of the approval process. Um, so you want to maybe, what we mean by produce three samples. Maybe you're making panels that have a buff color, like a tan color, and they're going to have a medium acid etch, for instance. Well, you're going to want to produce three separate sample panels, maybe even more, for the architect to come look at and go, okay, well, I really like this. And once you've selected the target aesthetic, then you give them examples of, okay, well, if we got the acid etching a little lighter, this is what it would look like. If it was right on, this is what it would look like. And if we went a little bit too heavy, this is what it would look like. And ideally, you come up with three samples that all three get approved. When you put those three next to each other, the variations are not significant enough that the architect is okay with it. And they approve, okay, we're okay with this range of finish. Anything within the range of lightest possible to heaviest possible etch, we're okay with. We're okay with this amount of air bubbles, or we're okay with, there's all kinds of different things you could potentially include there to get them to say, yeah, we're okay with that, or no, we're not. And once you arrive at a decision, you keep those panels in the yard, keep those in the near the finishing area, so that the people doing the finishing can regularly look at those as a touchstone to say, okay, we're not drifting too far away from what the target is. They can compare visually. Here's the panel we're producing for the day, and just over my shoulder are the accepted panels that the architect came and looked at. So let's make sure we're matching those as best we can. You want to always create a checklist of items that were reviewed with the architect and that were approved or not approved. And it's usually always included in the specifications that the owner and the architect are responsible for inspecting and approving that initial production. So, what even after they've uh, approved a sample, they still are coming out to look at the first two or three panels that are created to make sure, okay, now we're seeing it at scale. Yes, we still agree that it looks like what we thought. And before you make 30 panels and get half of those shipped to the site, and then they decide, no, this doesn't meet the aesthetic that we were going for. Now you've got a lot more money that's being wasted. So those things, obviously, when I talk through that, hopefully you hear that and think, oh, yeah, obviously those things are important. But we haven't really talked about yet what can we do to make sure that, um, that we're meeting the requirements of the project and that we're being consistent with our production practices. Make sure you have people in the yard and people on the stripping crews who are trained properly on how to handle the panels. You can do the best job possible in casting and setting up forms and then the finishing operations, but if you've got someone who's not being careful as they're transporting those components around the yard or even out of the form and they damage that finish, then all that effort is for naught. So mishandling is something that's very common that we'll see in storage yards where something got chipped or spalled because it wasn't handled properly. There are acceptable repairs. This also needs to be something that is presented to and approved by the owner or architect. That, okay, if something has to be patched, this is what it will look like, and we'll blend it in as best we can, but it may still be a bit visible to the discerning eye. That needs to be something that's shown to them. Otherwise, any panel that ever had to be patched might have to be fully rejected if the architect doesn't approve that process. And then we talked about this already as it related to the quality of our concrete, but not just the strength and integrity of the concrete, but this is also true for the aesthetic, that we are consistent in our production processes, from anything from materials sourcing to batching procedures to placing operations to how we're using the vibrators to consolidate the concrete to our curing methods and curing time, as well as our finishing operations. So all of those things, we have to be consistent day to day so that we get a consistent outcome. Any of those can have an effect on how light or dark the concrete ends up curing out to. Slight changes in materials can obviously have an effect on that, but also curing time. When was the accelerated curing started? What was the water cement ratio? There's a little diagram in your book that I've always found helpful. I don't think we have it on the screen, but if you turn to page 8.5 in your book, figure 8.3, there is actually 8.2 and 8.3. 8.2 is a list of, and this is not I wouldn't say this is a comprehensive list of everything that could ever be included on a checklist, but these are some common items that you might want to, and in most cases, should review with the owner or architect and agree upon all of these items beforehand. So things like color, texture, the depth of the etch, the amount of coarse aggregate, the shape, the geometry of not only the overall panel but also reveals and returns and things like that. Anytime there's veneer or any other special finish, make sure they understand what those things are going to look like. And then also the natural weathering. It's probably not a bad idea to, let the owner or architect, if they've never worked with precast before, to go take them to a few different buildings that were produced from precast that are now 5, 10, 15 years old, and let them see this is how panels age, and this is what they look like after a few years. And that way they can see it and kind of get their arms around it and be ready to say, okay, yeah, we know what we're getting into here. We know what this is going to look like. There's also some other things, maybe on a more immediate path would be things like, dirt streaking from being in the yard, staining from the way you're having to store it from the rack, locations of the drip edge. And then you're also saying, okay, well, here's our most experienced finisher. They're going to be responsible for the approval in-house, and then you'll have a representative. They'll be responsible for on your end. So there's a lot of decisions that need to be arrived at. What I was going to point out to you in figure 8.3 is just the drastic variation in color that you get, not only from a wet to dry. So if you look at those 4 samples up in the top that are dry samples, those are the same, nothing is different about the concrete mix. The difference is the water cement ratio, and this is just a cement paste, no aggregate. So cement paste, cement and water, the only variation being the water cement ratio. And you can see from a 0.3 to a 0.6 how drastically different those two are. It's night and day, literally. Almost black, and I understand this is grayscale, but almost black to very close to white, just from going from one end of the spectrum to the other on the water cement ratio. Contrast that with the variations you get from a wet versus a dry condition. Those same 4 samples are given in the bottom, but they are saturated. So they're a wet condition, and you can see even the 0.3 gets even darker. Even though it was already dark before, it gets even darker, and the others as well go from a very light gray to a much darker gray, just depending on how wet or saturated the concrete is. So we bring that up just to say the time and the environmental conditions need to be considered when decisions are being made on the final appearance of a product. You don't want to call the architect or the owner to come look at a panel the day after it's rained, and those panels are most likely still going to be damp and much darker. They may like the way that looks, but then in 2 months from now, when those panels are showing up on site and it hasn't rained in 3 weeks and they're dry as a bone, they're going to see something much more like what you see in the top, where they're much lighter, and they may have a hard time believing that, wait a minute, these are the same panels. I can't believe this is so much lighter. So they need to understand, as I think you would hope most people do, that when concrete's wet, it looks darker. But my point in all that is that the water cement ratio can have an effect, as well as the environmental conditions of the panel. Architectural plants, at least most architectural plants, are using white cement to create white concrete. And as you might imagine, white concrete can be very difficult not only to produce, but especially can be especially difficult to maintain, to clean, to get to look right, because every little imperfection shows up because of the color. So you want to be careful not to use any materials that are going to stain the surface of that concrete. You may never get it out all the way. And when I say materials, I'm talking about anything from the condition of your reinforcement, if it's got a bunch of rust on it, or the wire ties that you use, or the condition of the forms, the form release agent that you use. All of that can stain that white concrete. You also want to make sure you clean your batching and handling equipment thoroughly, so you don't get any leftover gray or red or green or black concrete from the last architectural mix you batched, getting mixed into that white, because it'll take that color readily, and all of a sudden what might look white to you standing alone, when you put it next to the panel you produced yesterday, may be quite a drastic difference in the overall color. You also, most of the time I see architectural plants do this, but I have seen time to time not doing this, and it does create an issue. If you've got white concrete, you want to suspend or hang that reinforcing cage down into the concrete, so that you don't have those little gray plastic chairs sitting on what will soon be the finished face of the concrete. So you've got white concrete with little gray dots spaced at some spacing once you etch it. That wouldn't be great. So obviously, suspending the reinforcement is best, and certainly don't use metal chairs that can then rust and stain the surface as well. The next 2 items here, so actually the next 2 slides, this slide and the next slide, go ahead and be turning to this section in your book if you're not already there, 824, beginning on page 8.7. You should have received as part of your materials in your email when you got materials for the class, there should have been a little document that I'll kind of go over with you briefly in class, but there's more information on this. that we'll get to in just a moment that deals with how to deal with efflorescence once you have it. So some of you may be asking, well, what is? I've never heard of this before. What's efflorescence? Um, Basically, it is a white film that shows up on the concrete and makes it look bad. And generally, once you see it the very first time, the very first appearance, it can be cleaned. Um, if it keeps recurring on the finished concrete in service, it usually means you have a moisture problem, an environmental moisture problem, where water is being continually in contact with the concrete, and it's getting into the concrete and then evaporating and making its way out. Is usually what that means. um, on a more technical level, if you ask the question, well, what is it? What causes it? What's happening is you have these water-soluble salts that are present on a molecular level in the different materials that make up concrete. Those could be present in either of your aggregates. Sometimes those are present in the cement, usually not, but could be. Sometimes those are present in the actual mixing water to a small degree. And so there's two different types of efflorescence. You've got primary and secondary. In both cases, the same basic phenomena is happening. Water is migrating to the surface and bringing with it these salts that have been made soluble in that water. And so as that water makes its way to the surface, it then evaporates and it leaves those salts behind as a white powder looking discoloration on the surface. The difference between primary and secondary is that primary, that's happening with the water that was present because of the concrete production process. So the water that was present on and in the aggregates, as well as the mixing water, as that piece continues to dry out and cure over a period of months, that water is all sort of slowly but surely making its way to the surface. And you might start to see that primary efflorescence show up even while panels are stored in your storage yard. Much more common is secondary efflorescence, which is where these calcium carbonates and bicarbonates, these salts, in other words, are in the concrete, but they're not doing anything to hurt you. But if it's a wet environment, you get rainwater or spray from the ocean or something like that, continually making its way on concrete. While it's in the saturated condition, it goes into the concrete, and then as it dries out, it pulls those salts out with it. So that's secondary efflorescence. Just drilling down a little deeper, these calcium hydroxide, these salts, typically are more soluble at low temperatures. So it's sometimes more prevalent in cooler environments just because these salts are more soluble in those environments than you would see, like in Arizona or somewhere. There's four things that have to be present for this to happen. As I've described the sort of the physical nature of this process, you've probably already kind of maybe picked up on some of these. Well, first, the soluble substance, in this case, these calcium hydroxides, that has to be present. Secondly, it wouldn't show up if that was present, but there was no moisture. So secondly, moisture has to be present. That moisture has to be able to get into the panel and then move toward the surface and carry those calcium hydroxides with it. And then finally, that moisture has to be able to evaporate in order to leave those salts behind. If you can eliminate any one of those parts of the process, either in production or in service, then you'll eliminate this efflorescence altogether. There are some things you can do from a material standpoint to minimize it. You can use very low alkali cements, so cements that have less than 0.35% of Na2O. Making sure you use clean washed C33 sand, and be extra careful with limestone-based aggregates. Obviously, use clean mixing water. There are plants out there. Different states have different incentives for recycling wash water and using less water. And while that's overall a good thing, you definitely want to make sure the right um, checks are in place to make sure that water is still acceptable if you're using wash water. There are limits on different particles and contaminants that can be present and it still be allowed to be used. So some of these calcium hydroxides may be present in your wash water if you're recycling, or even if you're getting it from a municipal source. Sometimes things happen there as well. So make sure you know the quality of your water. Um, we've got additives on here. I'm not aware of any additives that have been shown to be consistently successful in eliminating efflorescence. I'm sure there's things out there that you can add to the mix that will maybe slow it down a little bit, but if you could come up with a good one of those, you could most likely make a lot of money. You want to make sure you have a very low water cement ratio and good consolidation and thorough curing. And hopefully those things are obvious when you think about them. The less water, a low water cement ratio means overall you have less water, which means less voids once that water evaporates, and it means less water to carry those calcium hydroxides to the surface in the first place. And then making sure you've got good consolidation, so you're eliminating that entrapped air that would serve as a pathway for that water to get in directly, and then having a thorough curing process so that you eliminate any plastic shrinkage cracking or any rapid moisture loss that might facilitate this in happening. Using air entrainment will help for the same reason that it helps eliminate freeze thaw damage. It gives the water a place to go without going all the way into the concrete through this entrapped air or through possible cracks that have been caused by freeze thaw stresses, internal stresses. And then something that we don't maybe think about a whole lot in precast plants, but using a surface sealer, something that you spray on and it has to be maintained and maybe even reapplied throughout the life of that panel or product, that will prevent water from getting in. Just like you seal your deck, you can seal concrete as well. Before I go much further, there is if you look on page 8.12, about the middle of the page, just above section 8.2.5, that paragraph there, it says, more information about efflorescence is available from PCI. A paper titled Efflorescence on Precast Concrete provides more detail about what efflorescence is, what causes it, how to minimize it, and, not covered in this discussion, how to remove it. I'll just give you some, like the quick overview of that just for your own personal benefit, but you should have access to that. If it wasn't part of your materials, it should be available on the PCI website. But it's basically, once you have it, once you notice this efflorescence on a piece, it's going to be something that you, in many cases, are going to want to try to remove. And the methods to try to remove it, you could probably guess at what some of those are. The first step might be we'll just use a stiff, bristled brush to try to scrub it off. See, will it come off if you scrub on it a little bit with a brush? Something that's not going to damage the panel, but that is stiff enough that it might remove that staining on the surface. You can also try an abrasive blast with something like baking soda that's not so abrasive that it will damage the surface of the concrete, but it may take off the efflorescence. If that doesn't work, you can maybe up the ante a little bit by scrubbing it with a brush and then using a low pressure washer to try to rinse that off. You could use chemical cleaning compounds. There's different detergents or even phosphoric acid or other chemical cleaners that can be used if they're used in the right way. And then that's basically the extent of it. If you can't get it to come off using any of those, then you may have to just do the best you can and get it cleaned, and then go back to the drawing board and look into some of these items to help prevent it in the first place. One thing to think about, especially with secondary efflorescence, is um, once you start blasting or doing anything that's going to speed up the deterioration of that surface layer, if you're sandblasting or pressure washing, um, potentially you could open up small hairline cracks that were there but were covered or closed up, or even exposing entrained or entrapped air bubbles that were just below the surface. Well, now all you've done is potentially made the problem worse in the future, or come back more quickly in the future, because now that water has an even more direct pathway to get in and then back out. So it's one of these problems where efflorescence doesn't necessarily represent a structural issue like that, where it's going to affect capacity or life safety. It doesn't look great, but if it's on the side of a bridge girder, do you really care that much? If it's on an architectural panel, you may have a bigger problem. So you want to make sure you know what the requirements are, know some things about some of these things you can do to minimize it, especially if the area you live lends itself to causing this. I'm going to stop there briefly just to see if there are any questions that have come in before I go too much further.
We did have one question come in. Does differential camber matter if the DT or hollow core surface is going to be topped, and why?
I'll say maybe. If the differential camber is just a little bit, maybe it's a quarter inch, or if it's just out of what the project specs say, and you're putting a thicker 2 or 3 inch topping slab on it. Obviously, yeah, to your point, that's going to cover up any differential displacements in the camber from piece to piece. But if, let's say, the differential camber was 1.5 inches, and you're supposed to be putting a 2 inch topping slab on it, well, 2 inches from where, right? Are you measuring 2 inches from the double T that's got the higher camber? If you are, then you end up with much thicker topping slab than you're supposed to have. If not, then you end up with much thinner topping slab, at least across that double T. So it can create issues. You're really just pushing the tolerance issue down the line further, right? And so now you've got a tolerance issue with how thick your topping slab is. And by the way, that topping concrete weighs something, right? So if it if those differential cambers represent the need to add all of a sudden another inch of topping slab, you've now taken out an inch of that residual capacity that those double T's had, because you put it back as a cast in place dead load. So those things have to be considered. To your point, small variations can be masked with secondary pours, but I wouldn't depend on that, because you could end up creating other issues. Were there any other questions, Lauren, or was that the only one?
That was the only one.
Okay, so let's move on from efflorescence then, and let's just continue talking about just general discoloration, not necessarily discoloration caused by efflorescence, but discoloration that could be caused from any number of other issues in your plant. So we want to make sure we're using, we've said it before, I'm saying it again now, consistent materials. Make sure your aggregates are regularly mixed and blended so that you're getting a good distribution of particle, size, and shape and color. Make sure you have a consistent water cement ratio. Just because your water cement ratio meets the project specs doesn't mean that one day you should produce a panel that's got a 0.4, and the next day you produce a panel that's got a 0.32. Well, they're both less than what's required, but as you saw in that little swatch in your book, that the difference in 1/10 of a percentage point of your water cement ratio can represent a pretty big difference in the overall color of the piece. You want to, as with anything you do, have consistent mixing and placement procedures. You want to maybe have a curing enclosure that's going to protect that concrete from the ambient environment, to protect it from contaminants or lack of moisture or cooler temperatures. Don't touch the surface if you can help it while it's curing. You want to obviously not expose the surface to mud or oil or melting snow or any other contaminant that it might come into contact with when it's in your plant. So there's a lot of things that you can do, and if you've been doing this very long, you kind of know, especially with your specific individual production environment, you know what the pain points are. You know where you typically have issues, or at least you should, and use that. Be wise about the decisions you make. We want to avoid storing panels in this particular way because we know that for that color and finish combination it causes staining problems or whatever. So you can minimize discoloration in any number of ways, and it's really a top to bottom approach. You're controlling materials all the way to storage. Cracking obviously is another thing we want to be able to control. There are a couple of different resources available to you, these crack reports that are from the PCI journal. Those should have been part of your materials as well. So if you don't know what I'm talking about, go back and find that email. They should be there. And if they're not there, as Lauren pointed out at the top of the hour, get with her and she can get that stuff to you, or can point you to where that can be found. You want to use those resources, and I'll show you some examples here in just a minute. But you want to use those resources to help you evaluate whether or not a crack represents a problem or not. It's kind of an industry standard saying that concrete cracks. If you see concrete, it's got cracks in it. It's just a matter of what caused the cracks, and do those cracks now represent a deterioration of the load carrying capacity of that member, or will they continue to allow that component to be deteriorated over time, such that at a future date maybe its structural capacity will be compromised. So you want to be able to look at a crack, and eventually maybe you'll get to the point where you can recognize, oh, well, that shaped crack in that location means this. But until you get there, you've got resources available to you that'll show you what some of those things might look like. And on the next couple of slides, I'll show you that. But things like measuring the crack width, the extent of the crack, how long is the crack, where does it start and stop, is it seemingly randomly shaped, or does it run in a relatively straight line from point A to point B? Is it located in a specific part of the panel? And when I say measure the crack, we don't want to just go out there and just kind of ballpark it and say, well, it's about a 16th of an inch. You actually want to use a crack comparator to measure those cracks to a very tight tolerance, so that you can have a really good idea of the degree of magnitude of what those cracks represent. So a crack comparator, if you don't know what that is, it's a plastic card about the size of a credit card. It's made out of clear plastic, and on at least the one I'm holding one in my hand right now, just so I can describe everything to you. On the left side, it's got little black lines of graded width, varying width, all the way from 0.004 of an inch all the way up to 1/10 of an inch. So it gives you these black lines. The idea is you would lay this clear card over the concrete surface, lay it directly flat over the top of the crack, and then you would kind of move the card until you find the line that best matches the width of the crack, and that tells you, okay, well, that crack is 6/100ths of an inch wide. The other side has the same thing, but in millimeters. And so that'll let you give an accurate measurement, or obtain an accurate measurement of those crack widths. And anytime you have cracking like that, you want to report it accurately. So give maybe a little diagram, a little sketch that shows, well, here's the double T, and the crack ran from the bearing point all the way up the stem about 5 feet, give a dimension, kind of show where it runs, so that those cracks can be evaluated. On this next few slides, we'll show you what some of these different what some of these different resources provide. So those two crack guides that I mentioned, this is the way the information is given to you. So this is a piece of hollow core plank, and there will be several pages for hollow core because it'll show you, well, this crack is a transverse crack that's on the top of the hollow core plank that runs directly perpendicular to the span, and it runs right across the top. And the way these are formatted is it'll give you the cause, and in some cases it gives you multiple possible causes and the corresponding prevention of that cause, and then the effect of the crack and potential repair procedures. So just to kind of look at some of these, this one says that this could be caused by longitudinal shrinkage. So maybe you had a little bit too much water in the concrete, or it was the conditions caused the moisture to evaporate quickly, or it could be contraction due to delayed tensioning after uncovering it. So the tendons haven't been released yet, but the concrete starts to shrink, so on and so forth. And then it gives you the appropriate prevention method here. The maybe the most interesting, or I would maybe argue important part of this is, what is the effect? So this one says potential shear capacity reduction if that crack occurs at the end of the plank can have a significant effect on shear and moment capacities of cantilevers. Reduction of moment of inertia in center of member can cause camber differentials and excessive deflections. And if you don't know what all that means, it means that this particular crack, depending on where it occurs, can have a significant, it can be detrimentally significant to the load carrying capacity of the piece. It does give some repair procedures here. So in some cases, these cracks can be filled and patched. Here's, again, this is still double T, but it's a different crack pattern. So this one shows up on the side and propagates back a few feet. And again, it's giving you the cause, the prevention, the effect, and the repair. This one, flange crack between the stems on opposite sides. So you can see how it runs sort of on the edge of this stem, and then about midway through it switches sides and runs here. There's only one cause of this. It's torsional stresses. Now, the cause of the torsional stresses might vary. It could have been something that happened during stripping or during handling. Most often we see this because of an issue, dunnage that is settled differently from one end to the next. And so the storage could actually be causing these torsional cracks. Obviously, the solution to that should be obvious. Change your procedure. Make sure you're storing this on level, rigid dunnage, or use the appropriate lifting devices. The thing here, this says this type of crack usually has no effect upon the load carrying capacity, so that's good. But roofing adhesive potentially could seep through and contaminate any exposed areas. It could also be a water infiltration problem if it's something that's going to be exposed to water. So the crack may not have any structural implication, but it could cause other problems with the overall functionality of the building. I won't go through all of these, but this is just to show you some different examples of what these crack guides provide. Okay, what questions do you have on Chapter 8? Or actually anything that we've covered to this point?
No questions have come in yet.
All right, it's right at 2 o'clock Central Time, so why don't we take about a 15-minute break, and we'll get started back at about 2:15 Central. If you've got questions, send those in, and we'll take a minute or two when we start back to make sure we get all of our questions answered.
All right.
All right, we'll take about 3 or 4 more minutes and get started back. So get finished up with whatever it is you're doing and get back ready, and we'll start back here in a few minutes. All right, I'll go ahead and ask now. Were there any questions that came in during the break that we need to take care of before we move into chapter 9?
Yes, we did have one question came in. They asked, do they expect us to know all of the crack issues?
No, no. So the crack issues, those are things that those are provided to you as a resource. The main thing you need to understand is that cracks, different cracks have different effects on the functionality of the product, and that they need to be evaluated by the engineer to make a call on whether or not those things, first of all, need to be repaired, and if they need to be repaired, how are they to be repaired. And in some cases, those things have to be just rejected or scrapped if there's nothing that can be done structurally. So no, you don't need to memorize what all the different cracks mean or anything like that. Just be familiar with the fact that you have them available to you, and maybe how you would use
All right, that's the only question that came in.
them. Okay, let's move into chapter 9, which will be our last chapter for the class. And this will go pretty quickly. A lot of the information will be a review from level 2 especially, but there will be a lot of new information as well. We'll dive a little deeper into welding symbology and how to read a weld diagram, and what those things mean and what they're telling you, how to properly specify a weld, and different things about visual observation of welds, and making sure those welds are adequate. The first thing we'll talk about is the carbon equivalent. This is something that it's either given to you directly on your reinforcement mill certs, or there will be enough other chemical composition information given to you that it can be calculated. There are two different main types of steel that you should be familiar with, and that you're probably using at your plants. Probably every plant is using at least A615 steel. That's just the regular, plain old grade 60 rebar. The alternative would be it's still the same tensile strength of steel, but ASTM 8, what we call shorthand, 706 steel. And this basically just means that the chemical makeup is such that it has a slightly lower carbon equivalent on average. Both types of steel can be welded. We give A706 steel the shorthand name of weldable rebar. That is not intended to imply that you cannot weld A615 steel. It just means it is maybe a little easier to weld A706, and we'll get into why that might be. The AWS, which is the welding specification, there's two different ones. There's D1.1 and D1.4. D1.4 is the structural welding code for specifically for reinforcing steel. And in the AWS D1.4, it gives you these two different equations for being able to calculate the carbon equivalent for either A615 steel or A706 steel. It is generally true that on the mill certs for your reinforcement, if you're getting A706 steel, most of the time, I couldn't tell you the last time I saw a mill cert that didn't just give you, here's what the carbon equivalent is. But if they didn't give it to you, you could calculate it using this formula here. So you see this formula is much more complicated and much longer than the formula given here for calculating the carbon equivalent of A615 steel. It would be much more common to look at a mill cert for 615 rebar and not see the carbon equivalent given to you, but you could easily calculate it. The formula is simply the percent carbon plus the percent manganese divided by 6. And that's going to give you a number in decimal format, less than 1, that you can then use to compare to some requirements that are also given in AWS D1.4 that relate to the preheat requirements for that specific base metal before it can be welded. The reason those preheat requirements exist is to prevent the embrittlement of the steel from rapid thermal shock, an increase in the temperature from the welding procedure, or a rapid decrease in the temperature from a localized temperature of the welding if you're in a cold environment. So the carbon equivalent is important because it tells you whether or not, first of all, do you have to preheat? And if you do, what temperature do you have to preheat to? And you need that carbon equivalent. You need to check that whether you're using 706 or 615 steel. It's just that the requirements are slightly different. I was going to see if we had that. We don't have the chart, but for the sake of helping you understand how to use it, turn to page 9.4 in your book. Page 9.4, and the table is actually table 9.4 on the same page. Give you a second to turn there. So page 9.4. You'll see that table is called minimum preheat and interpass temperatures. And it tells you there, this is from the AWS D1.4. So the way you would use this table, and somebody might ask, so I'll go ahead and say now, you don't have to memorize this table. I don't know if they'll give you a question about any of this, but if they did, they would give you the table to be able to compare to and determine what your preheat requirement was for that specific set of given information. So what you do is you would either calculate or go get your carbon equivalent from your mill cert. You would also know what size bar it is that they're wanting to weld. And you go into this table, and so it says carbon equivalent range percent, and that's on the left-hand side. And then you've got the second column of information is the size of the reinforcing bar. And third, this is the shielded metal arc welding with low hydrogen electrodes, um, gas metal arc welding, or flux core arc welding. So this is specifically talking about weld types that are not like a stud gun, where you're shooting the studs on, which we'll talk about a little bit later. So these are the typical types of welding you would see for doing something like this. And so I'll give you an example. Let's say you were dealing with a number 6 bar, and it was A706 steel, so it had a relatively low carbon equivalent, so it was like a 0.38 carbon equivalent. 0.38 carbon equivalent, number 6 bar. You would go into this table, and you'd start with finding which range of carbon equivalent you fall into. And so for a 0.38, you'd be at the very top, up to 0.4. And it says size of reinforcing bar up to 11 inclusive, 14 and 18. So in other words, every size bar that we would realistically be using in a precast plant. And it says that the preheat temperature is none or 50, which most of the time it'll be that temperature anyway, unless you're in a really cold environment. There is a footnote, and those footnotes are below the table and continued on to the right-hand side of the page opening. It says, when the base metal is below 32 degrees Fahrenheit, the base metal shall be preheated to at least 70 degrees Fahrenheit or above and maintained at this minimum temperature during welding. Basically, what the welding code is saying there is, don't set up your welding operation in the middle of Buffalo, New York, out underneath a covered roof with no walls, so that in the wintertime you're out there trying to weld, and the ambient temperature is so low that even if preheat isn't required for the bar, it's going to cause rapid cooling of the bar, which could cause that bar to be embrittled just as much as a rapid heating process might. So it's giving you a caveat there that only 50 degrees is required for up to 11 inclusive, and then for number 14 and 18, you have to at least heat it to 50. But for either of those, if the ambient temperature, which you would assume the base metal would be, if it's just sitting out in a rack, it's going to be the same as the ambient temperature. So 32 degrees, it has to be heated to at least 70, just to make sure that you don't end up with that rapid cooling. Rapid cooling. So let's say you had some 615 steel then that had a carbon equivalent of 0.47, and it was a number 8 bar. So 0.47, number 8, you'd be in the 1, 2, 3, you'd be in the third row down, so over 0.45 to 0.55 inclusive. And I think I said number 8, so you'd be the middle there. So you'd have to preheat to 50 degrees. All right, let's say you had a carbon equivalent of 0.6, and you were dealing with a number 7 bar. So carbon equivalent of 0.6, number 7 bar. You're in the fourth row down, and you're in the middle. So up to 6 is the first one, 7 to 11 is the second, 14 to 18 is the last. So you're a number 7 bar, so you have to preheat to 200 degrees. So now we're starting to see some pretty stringent implication here, that you have to preheat that bar to 200 degrees before you can weld it. And then it would be a pretty rare circumstance, but let's say you got some rebar that you had a given carbon equivalent of 0.75. Anything 7 to 18 has to be heated to 500 degrees, which would be pretty difficult to do and maintain it at that temperature. One thing to note, if you get mill certs from your rebar supplier and they are not giving you chemical data, they're not giving you any of these chemical compound percentages, such that they're not giving you the carbon equivalent, but they're also not giving you the information to calculate it yourself, you have to assume worst case. And what I mean by that is you have to assume that it has a carbon equivalent over 0.75, which means if you're going to be welding it, you have to preheat it to 500 degrees if that information is not made available to you. So it's important that you know what information is being given on your mill certs, that you know how to use it, and that you know what the implications are of your different production processes. We don't ever, especially with our reinforcement, want to cause issues that might embrittle it and cause an abrupt failure that is not predictable. One thing I'll say here, because I always get this question, what about tack welding? It's in the name. Tack welding is welding. And so the same heat, the same thermal input is being applied to that steel. So whether you're tack welding it or welding a 24-inch long bead, you still there's still an opportunity that you might embrittle that steel. So tack welding is welding, and the same procedures apply that would apply to any other kind of. This is just a summary of the footnotes that you'll see in the below the table. So I'll just kind of briefly go over those. This is for welding of rebar, this D1.4. D1.1, which is the other welding code that I mentioned, is specifically for structural plate or shape. There are requirements for welding that stuff as well that you should know about and be familiar with. But we're specifically talking about welding rebar. So the first footnote is telling you if you're doing anything to plate or structural shapes, make sure you check the AWS D1.1. And there's two different tables, and you've got to use the more stringent of the two. So D1.1 has a table, D1.4 has one. If you're welding a bar to a plate and the plate has a higher preheat temperature, that's the one you've got to abide by. Footnote number 2 says welding shall not be done when the ambient temperature is lower than 0 degrees Fahrenheit. So, if you're, again, I'll use that extreme example of welding in the middle of winter. You don't want to do it when you're below 0. So there's two different requirements. There's one requirement that says welding shall not be done when the ambient temperature is lower than 0. And then that fifth one we already looked at, and it says when the base metal is below 32, it's got to be preheated to 70. So if it was 0 degrees outside, you can't preheat the bar to 70. It just says you cannot weld when the ambient temperature is lower than 0 if that's the environment you're welding in. Now, if you're in a nice warm weld shop, obviously the ambient temperature inside that weld shop will be something probably closer to 60 degrees, so you're probably fine there. After welding is completed, the bars need to be allowed to cool naturally to the ambient temperature. Any kind of accelerated cooling is prohibited. Again, we're trying to ensure that we've got these long, slow ramp up of temperature and cool down periods so that we don't embrittle the material, the steel. And I already mentioned number 4, where it is impractical to obtain chemical analysis, the carbon equivalent shall be assumed to be above 0.75. And that's just saying if you don't know what the CE is, you have to assume worst case and preheat to 500 degrees. All right. There's a few things that I'll point out to you. I think I've got all these marked up in my book. So I'll start off by saying generally there's specific electrodes that have to be used with different grades of steel. Generally, E70 needs to be used with grade 40. E90 electrodes need to be used with grade 60. And anytime you're doing A36 steel, it should be E70. There's a paragraph in your book that is worded very specifically. And because it's worded so specifically, it actually makes it incorrect. And I'll show you what I mean by that. So the first thing I'll do is call your attention to page 9.5. There's a section at the bottom of that page in 9.1.3. It says 9.1.3 electrodes. I'm going to read the sentences to you that I want you to modify, and I'll tell you what to change them to, and then I'll tell you why we're changing them. Okay? The second sentence there, it says, it shows that E70XX electrodes must be used with grade 40 bars. Okay, so far so good. Then it says E7, and it says E80 electrodes with ASTM A706 bars, and E90 with grade 60. Okay, in both instances where it says E80 and E90, I want you to mark out E80 and mark out E90 and write in E70 so that it should read, it shows that E70 electrodes must be used with grade 40 bars, E70 electrodes with ASTM A706 bars, and E70 with grade 60. All right, let's skip down a couple of sentences, and I'm going to have you make one or two more corrections, and then I'll explain why we're correcting this. I think it's the second to last sentence on the page. It says, if a grade 60 bar is welded to a plate of A36 steel, the electrode must be matched to the bar. And I want you to mark out bar and write plate. So it should read, the electrode must be matched to the plate, or E70 in this example. So mark out E90 and write E70. So the reason that we're making these changes is because in precast plants, it's very, very rare that you would be making what's called a butt weld. More commonly, you're producing plates and embeds and things that have what we call like a lap connection, where you're laying a bar down on a plate and welding on the sides of it. And in that condition, E70 electrodes can be used with grade 60 if it's a lap connection. The statements as they were previously written in the book is assuming a full penetration butt weld, which is just not something, for one, it's not something that's very practical to perform, and two, it's not something that's common at all in a precast plant. So for the sake of this book, it really should have been specific to a lap weld connection, and E70, for anywhere that electrodes are mentioned in that paragraph, it should read E70, assuming that it's for a lap connection. You might make that footnote that those changes are assuming a lap connection. So hopefully that's not confusing for you. Hopefully that makes sense. It's important with welding that we take care of the materials that we're using to weld, namely our electrodes. So the way that we store those, the way that we use them, the ambient environment, it's really important that those electrodes are not kept in a moist or humid environment. They should be purchased and stored in hermetically sealed containers. And then once those containers are opened, it's required that they're stored stored in a very specific type of an environment, so that they remain dry. If they get wet, a lot of fab shops will just throw them away. If they get wet, the AWS code actually allows you to re-dry those one time by putting them in a 450 to 500 degree oven for a certain amount of time. They can be dried in that manner. If they get wet again, you have to throw them away. So it's important that we take care of them. If they're damp or moist when you try to use them, it could degrade the connection and cause an incomplete weld. I guess I'll stop there to see if there were any questions on what we've covered so far for welding before we keep going.
We have a couple of questions that have come in.
Okay.
The first one we have is table 9.4 for both A615 and A705 or A706.
Yes. Yeah, so that is simply a welding of rebar. Preheat requirements for welding rebar, whether it's 615 or 706. Just to remind you, the only difference between the two is 706 typically has a lower carbon equivalent on average than 615, which is why we commonly consider it weldable. Because if you look, the implications of a lower carbon equivalent is a much, much lower, or in most cases even, uh, there is no preheat requirement for the bar sizes we're looking at. It's when you get into those higher carbon equivalent numbers that you see with 615 steel is where you start to get into the more stringent preheat requirements. So yeah, the table is for both types.
Okay, and then the next question we have on here is your slide says E90 with 60 bars. Why did we change it in the book?
The slide is patterned after the book, which assumes a full penetration butt weld. So if you were welding, like for that specific example, if you were welding grade 60 bars, and if you don't know what a full penetration butt weld, it means like if you had a bar, two bar ends, and you stuck them together, um, one end touching the other, and you actually prepared the end of that bar by like grinding it into like almost like sharpening a pencil, not quite that extreme, but you would prepare the edges of that, put those two together, and then fill that with weld so that you get that's what the full penetration is. The weld is penetrating the full thickness of the base material. Um, in that instance, there's much more opportunity for that weld to fail versus a lap weld where you take two bars and you lay them side by side and weld a certain length of that lap. So the reason for the more stringent, like having to use an E90 electrode, is because there's more opportunity for that connection to fail. So again, the slide, just like the way the book was printed, is assuming a full penetration butt weld, and that is just not something that's common.
Okay, those are the only ones that have come in.
Okay. If you think of anything else, obviously you guys can keep sending those in, and we'll stop as needed. Um, let's talk then about visual inspection of welds. It takes experience. You obviously need to have seen the welding process before and maybe even done it yourself to be really good at this. But as auditors, we're looking at your welds as well, and we're not all welders. But generally, you're looking to make sure there's a lack of these geometric imperfections. You want it to be consistent shape and size and location. You're looking for cracks in the weld or in the heat affected zone of the base material or bar. So you obviously don't want any imperfections, don't want any cracks. You want to make sure those welds are free of overlap. I'll show you a diagram in just a minute. I think it's it's right here. I'll flip to that slide in just a second. But we're going to want to limit the undercutting to 1/32nd, a maximum of 1/32nd of an inch. If that undercutting occurs at a raised bar deformation or a rib, then you can go as much as 1/16 because you got that extra dimension there because of the rib. You're looking for porosity, so you want to make sure you don't see any what look like almost air bubbles or like kind of look spongy. Um, in addition to just basic visual inspection, you can also have radiographic testing, which isn't very common in precast plants. And if there's a major issue, you might think, oh, well, what can we do? Well, just grind it off and weld it again. Um, you can correct it by. It's a nice thing about steel is you can always just cut it and re-weld it. So that's usually what has to happen for these types of welding. Let's look at some examples of this. These diagrams I find helpful, especially if you've not seen some of these conditions before. There are examples given of acceptable and unacceptable weld shapes. So let's just kind of start at the top and work our way down. So top left, in section A, it says desirable fillet weld profiles. So imagine you're looking at sort of a side view of that weld where you've got material going up and material going left to right, and you're welding the two pieces together. If this dashed line is sort of the nominal weld size, then the gray shaded shape is representative of maybe what that weld might look like. So you can see there that that gray shading is bigger than, exceeds the nominal dashed line on all three sides. So we've got more weld there than is needed. There's no area where we're less than what that dashed line is. So that's desirable. And then alternatively, obviously this one, even though this one's concave a little bit, this one's convex. Both of them are good, consistent weld shapes that you might hope for. These two here are still acceptable, and so these are acceptable fillet weld profiles. They're maybe not desirable, so this is like perfect, or as close to perfect as you can get maybe. These are still okay, but maybe they're getting close to being where you might start to see some issues. And I'll point out the areas that are sort of deficient. So you see right here where the shape of the weld sort of starts to cut back, and it almost crosses the line where you're cutting into the nominal throat size of that weld. So that's kind of the problem there. On these other two sides, it looks pretty similar to these. So I don't really see any issues there. It's really this convexity right there that almost crosses the dash line. Same thing here. You got this little dimple that goes in that almost crosses the throat line. So there are some limits on those dimensionally that you don't have to memorize, but just know that there are limits on all the dimensions that are given here. So the degree of convexity, the dimensions from the outside edge to the middle of that dimple in the throat, those things have limits, dimensional limits. So that's desirable and acceptable. Then you get into some examples of unacceptable fillet weld profiles. And so let's look at this one here. This one's got what's called insufficient throat. So you've got this dimple that goes in, and it actually crosses or encroaches through that dashed line that represents the minimum shape of that weld. So that you can see why that would be a problem. This one here, this one basically just exceeds the limit. So up here it says note, convexity C, so that's this dimension, of a weld or individual surface bead shall not exceed the value of the following table. So depending on whatever these lengths are, these are the limits on the convexity. So this one, the issue is that convexity of that weld has exceeded whatever that limit was. This third one, excessive undercut. This one might be a little hard to see, but you can see right there behind my laser pointer when I move it, there's a little, what looks like notch that goes back into the vertical base material. That's just a line that represents, well, in this case, the heat was either concentrated too long on that point, and so it started to melt the material away such that you've effectively reduced the cross-sectional area of whatever that base material along that shear plane or tensile plane, so that you've reduced the strength of it by undercutting it. And I'll remind you that the limit for that was undercutting is limited to 1/32 of an inch, or if it's at a raised bar deformation, that dimension can go up to as much as 1/16 of an inch. This one here, the overlap where you've got weld that's overlapping more weld, that is not illustrated very well right here. I think it's better illustrated on the bottom right, where you can see, okay, these were two bars that were trying to be butt welded together, and you started and you made your way all the way around the back side of the bar, and you're coming up the bottom, and then you see here where that weld just sort of it overlaps. And it's not saying that you can't continue to weld until these are all melded together. What it's saying is this overlap is just, it's sort of deceiving because it looks like the two are connected, but it's really not. There's a cold joint between this weld and the weld underneath. So that's what is better illustrated, I think, by this diagram down at the bottom. This one, insufficient leg, hopefully that's pretty self-explanatory. It's supposed to be this triangular shape, and the weld didn't go up high enough on the vertical material. So that one's pretty easy to spot. We see this one maybe most often in a condition where you're taking a bar and you're butt welding it to a plate, like for a column base plate or something. And you've got these big column bars that have a relatively deep weld throat, so it's just hard to get that weld built up along that vertical surface without sort of putting that in a jig to help with that a little bit. This one, again, some of these are hard to illustrate, but you can see maybe the problem is illustrated here at the corner, the intersection of the two pieces of material, where you get this incomplete fusion, where the weld doesn't fully penetrate into the base materials all the way to the corner. So, these are illustrated with these other diagrams, but hopefully that helps you understand what some of the issues might be with these different weld types. Any question on that before we go to the next slide?
There haven't been any questions yet.
Okay. All right, so there's some additional requirements for welding A36 steel. So let me pause for just a second and say, anytime we're talking about rebar, for our purposes, rebar is grade 60, meaning the tensile strength of that bar is 60 kips per square inch. With plate and many different types of ASTM standard shapes, HSS tubes, pipes, wide flanges, channels, angles, those types of things, those are typically grade 36, meaning they're 36 KSI steel. So they're slightly lower tensile strength. You can get those different shapes in special. You can special order those with different grades of steel, but typically, if you haven't special ordered it, it's most likely going to be grade 36. Anything that has a thickness over 3/4 of an inch, you want to preheat, or you're required to. AWSD 1.1 requires that you preheat that material if it's over 3/4 of an inch thick. So if you're welding a bar, a piece of rebar to an angle that's got a 1-inch thick leg, you've got to preheat that angle. And so you'll need to go to the D1.1 to find out what that requirement is. Probably pretty rare, I would guess. I don't know that I've seen this very often, that a precast plant is welding stainless steel, but it is possible. You can weld stainless steel. It's a lot more difficult. It's a lot more involved process. Stainless steel has very low thermal conductivity, but very high thermal expansion. So what that means is heat doesn't necessarily pass through it very easily or quickly, but when it's exposed to heat, the material expands much more compared to regular carbon steel. So you want to be mindful of that. You have to use welding procedures that are a much lower temperature, so it can be a little more difficult. And that material has very specific properties. So with any of it, when you're doing stainless steel, regardless of the size of the material, preheating and post-heating are required to make sure that you slowly bring that material up to temperature. You perform the weld, and then you keep it heated, and you slowly let it decrease in heat so that you don't get any distortion of the material. And that last bullet point there, minimize heat. What that means is you're minimizing, you're welding at a lower temperature. So you're reducing the heat of the weld process to minimize that distortion. You can weld galvanized steel as well, but in case you were not aware, galvanizing is actually a process that the steel material is put through, it's a chemical process that applies that coating. So whether it's hot dipped or whether it's sprayed on galvanizing, when you weld it, you are vaporizing that chemical coating that's on the surface of that steel. So that that vaporized coating can be noxious. It can be poisonous. So make sure you have appropriate ventilation. You're wearing an approved mask to keep you from breathing that in. It's probably better practice to grind off that galvanizing on the surface locally, because if you don't, the welding is just going to burn it off anyway. You're going to have to recoat it with cold galvanizing spray after the fact anyway. So it's better practice to grind that off, so that you don't risk breathing that in. And you have to, obviously, what we've just described represents an adjustment to the welding procedure. Let's talk about qualification requirements that you'll find in AWSD 1.4. You'll hear us talk about and ask for things called WPSs. That's the shorthand for Welding Procedure Specification. In addition to the WPS, which, as the name suggests, is a specification that defines the actual weld that would be performed, i.e., a flare bevel weld of a piece of rebar to a plate, for instance, of a rebar of a certain size to a plate of a certain thickness, certain length, weld shape, location, all that would be defined in the WPS. In addition to that, the individual, the welder, the person conducting the welding, performing the welding, has to also be qualified. Not only be a qualified welder, but they have to be qualified on that specific joint. So if you've got a person who has taken and passed some welding certification, if they've never been tested on, for example, an overhead flare bevel weld of a bar to a plate, then they have to be qualified on that joint, not just for the specific type of welding, but for that specific joint as well. If you're interested, those different structural details and more information about this can be found in Chapter 3 of AWSD 1.4. The next page, let's see. Yeah, so I'm going to show you some examples of that. What else do I want to say about that for now? Maybe nothing. So there's some different things listed here. So WPS qualification for figure 3.5, that's this next figure that I'm going to show you. That's this joint right here. That's covered. So the procedure, the WPS, the weld procedure specification, is defined by the following. So section 6.2 of the AWS code. And just some basic truths about each of these. The WPS is qualified by testing. So someone has made this joint, tested it, knows what the strength of the joint is based on rules of thumb found in the steel code, and it's been certified. There's a table also on page 27 of that code that specifies the number and type of test that has to be performed, and we'll show an example of that. Figure 6.5C is the type of joint that must be tested for qualifying it. There's these tension and macrotech tests that are required. You want to use the largest bar with the highest carbon equivalent. So in other words, the more stringent preheat requirement. And there's a separate WPS that you should have on file for each process and position that you're going to be performing for your embed plates or other structural components for your product. Similarly, I won't go through all these point by point, but for the welder, there are similar requirements. The welder has to also be qualified by testing. So they're going to actually do a test weld. Somebody's going to watch them do it. They're going to test the joint, make sure they've done it correctly. There's a specific number and type. And then there's testing that happens on that as well. This is an example of how one of those joints might be detailed. So it's giving you information about the base material, about the bar, up here you see, or down here you see, this is a lap joint in an anchorage using flare bevel groove welds. So in other words, this is a plan view looking down. This is a section view looking through here, and you see, well, the flare bevel weld kind of has this shape where it's like a half circle and then a flat. So it's a half circle and then a flat, and so that's in most cases is sort of mimicked by the symbol, right? So this symbol, nowhere does it say flare bevel up here, but that's what that symbol means. That is a flare bevel symbol. The S is the size of the weld, so that's the dimension of the weld that's required. L is the length. So what length of weld is required, all that will be given to you in the weld symbol. We'll talk a little more about how to read those. Here's those tables that I was referring to. These just tell you the different um, number and type of test that's required for qualification of a weld procedure. This is another example of what one of those might look like. So you've got two bars coming together um, as a butt connection, but instead of just a butt weld, they've actually got these splice plates that are lapped over the two different pieces of rebar to keep you from having to do a direct full penetration butt weld. So you see in section, that's really what this looks like. You end up with 1, 2, 3, 4 flare bevel welds. And again, you see the symbol here, symbol here. Notice that the vertical flat line is always on the left-hand side, whether the leader is pointing to the left or pointing to the right. So if you take off the leader, the symbol should always look the same. You have weld size, weld shape or type, and then weld length. If the information is only on the bottom, so if there was nothing on the top of this symbol, then that would mean, well, you're only having to weld where the arrow points. Because you've got an arrow pointing here and an arrow pointing here, and the symbol goes on the bottom and the top, it's telling you it's required on the visible side and the blind side, so on the near side and the back side. That's why when you look at this section, you see it here and here, even though this was invisible in the view before. This is the number and type of test and welds qualified for welder qualification. So this is for the person. So the only point of showing you this is just to tell you that there's a specific amount of testing and type of testing that has to be performed to qualify either a procedure or an individual. More of the same, just another way of showing this information. So I won't spend much time on this other than just to point out that you got the weld symbols, you got the side view, the dimensions are given, and the welds are shown. Are there any questions on any of that before we get into stud welding?
There have not been any questions.
Okay, good. What I will say is that I believe it's in the TM 101, which is the level 1 and 2 manual. There are some examples in TM 10 or in level 2 that we talk about. We don't spend much time on that in level 3 because you've already seen it. But there are some examples in the TM 101 that show you what some of those different weld symbols might look like. If you're interested in boning up on that before the test, I would recommend going back and looking at those. Those can also be found in the AWS D 1.1 and 1.4. All right, in a live class, I would ask for a show of hands on who's seen stud welding. Usually it's about 3/4. It's usually over half of the class has seen this, but there's always a few people who haven't. So we'll talk about what that is. Stud welding is another type of welding. It's really different from what we're talking about when we're using a welding electrode to weld two different pieces of material together. With stud welding, what we're doing is we're taking a piece of steel and we're putting it in this apparatus, what the industry has dubbed a stud gun, and you put the stud in there, and it's got this little point on the end of it that you pass a current through that stud, and then at the same time, this happens in milliseconds. You push down, and while that current is being passed, you are you're heating the materials up so much that they become molten, and you're plunging the stud into that molten material locally. And so the two pieces of material fuse together in that way. This is what we call arc stud welding. And the reason it's called that is because you're creating an arc. You're passing a current, and it creates an arc between the two pieces, and that's how they're fused together. There's a couple of different components that are important to be able to do this without messing it up or creating an inadequate weld. There's something called a ferrule. It's a piece of ceramic that's small. It fits just around the diameter of the stud, and it's maybe somewhere between a quarter and a half inch tall. And what that does is it helps to concentrate the heat locally, so that, for one, you don't fuse the stud to the stud gun. It's an insulator, so it keeps that from happening. But it also helps control and make sure that all that heat and energy is focused right where you want it. One of the things that's important to remember about those ferrules is that because they are there, they cover up the weld. So after you've welded that stud to the plate, that ferrule is still there. And in order to perform an adequate visual examination, you need to break that ceramic ferrule off so that you can then see the weld and make sure that you have an adequate weld of that stud to the plate. Let me see if this other table is up here. So we'll come back to that in a minute. So you want to be able to perform a visual examination, and when we get to that slide, we'll do some examples of things you might see, of how those welds might look from the stud to the plate. This is what the setup might look like. So you have a welder just like any other welder, but the leads are a little different. You've got a ground lead that would clamp to the workpiece or something to ground it, and then you've got your welding cables that connect to your welding gun. And right here on the end of this welding gun, there'd be some guides that you would place that stud in, and it's just basically as simple as pulling the trigger and pushing down, and it'll weld the stud to the plate. Here is a diagrammatic view of sort of a step-by-step what's happening in the process. So this is the stud, and this is a threaded stud. You do have these threaded studs, but there's also, probably more common in precast plants, would be a headed stud, where you've got a smooth shank with a broadened head at the top. It almost looks like a big, tall, fat nail. And this is the little point I was talking about at the bottom that provides that connectivity so that the current can pass through both pieces of material. Here's the ferrule. This would be all the way around the stud. And so what happens is you position it so that the two pieces are in contact, but you haven't pulled the trigger yet. Then you pull the trigger, and the stud is going to be lifted, and so you're creating a slightly lifted. These are very slight distances we're talking about. So what it's doing is it's creating a spark, almost just like a spark plug in your car. And so that electricity is transferred between the two. And then in just a millisecond, that spark is created, the current's passing through, and then it's plunged down so that heat has made this material and the end of the stud molten, and those two things are plunged together. Then the gun is removed and the stud is left behind, and you have to break the ferrule off to be able to see the weld around the bottom of the stud. So that's the sequence. So there's a few things that you need to know about. There are some limits on the base metal thickness. The base metal thickness has to be greater than or equal to 1/3 the diameter of the stud. So the thickness has to be greater than 1/3 the diameter of the stud. And you can hopefully understand why. If you had a stud that was this thick and you're trying to weld it to a plate that was about as thick as my little laser pointer, it would just push through it, right? You want enough thickness of the base material that you can make it molten without going all the way through. That's the reason for that requirement. Just so you'll know, you might be thinking, well, do I not have to check carbon equivalent for this? The answer is you don't need to check it because these studs are provided to you. The material that's used to make these studs usually has a carbon equivalent of less than 0.3. So no preheat is required, or carbon content less than 0.3%. So no preheat is required. It's possible that if you're getting high carbon steel, that you may need to do some preheat. So definitely know what you're ordering. Are you getting standard studs? Or are you getting high carbon or medium carbon steel? In those instances, you would have to preheat. For low alloy steel, there is a minimum preheat. Again, stainless steel is sort of a whole different animal. We've kind of already talked about that a little bit in a different context, but there's over 300 grades of stainless steel, and you'll find that when you look at, especially the 300 series, there's all these different types of stainless steel, but the 300 series, those are weldable, but again, it's got that low thermal conductivity and high thermal expansion. So you've got to be careful with it, and there's different procedures that have to be followed. Anytime you've got base metal coatings and preparations, specifically like epoxy coating or galvanizing, you need to remove that. Otherwise, that arc is going to vaporize that stuff. Okay, so what are the quality control and inspection requirements for this? So first and foremost, you need to have trained operators. So who's doing the welding? Do they know how to do it? Has it been trained how to do it properly? You want to make sure you see that flash. So obviously they're still using a mask to protect their eyes, but you should see that flash. That's an indication that you're getting a good connection between the two pieces of material. And then you're doing a visual inspection, and you'll see these little, what we call burst patterns, where the molten metal has sort of spurted out between the little gaps in the bottom of the ceramic ferrule, and you expect to see that. That's an indication that the material was made molten, and you've got a good connection. At least that's one indication. There are some specific tests that need to be performed and documented. Generally, two studs need to be tested at the start of production of stud welded embed plates. As part of that testing of those two studs, you're going to measure the stud length. So you're going to look at table 9.6, so that's right here. So for different stud diameters, there are different length reductions that should be expected. So you're going to measure the stud length before you weld it, measure the stud length after, and you're going to record the length reduction and make sure that it falls into the appropriate category. So typically for precast plants, you're either welding 1/2 inch or 3/4 inch studs. So for 1/2 inch, you should expect a length reduction of 1/8. So you're measuring the stud length before and after, recording the length reduction. You're then going to remove that ceramic ferrule and inspect the weld all the way around. There should be a 360-degree flash pattern all the way around, ensuring that that stud was plunged down plumb and level and evenly all the way around. So there's the sort of visual inspection part. And then you're going to bend that stud from vertical to 30 degrees. You can use a hammer or like a cheater bar or a pipe sleeve or something like that to bend it over. If you are using a hammer, don't use a hammer if we're talking about temperatures of less than 50 degrees Fahrenheit, because if at those lower temperatures, the steel could be embrittled, and so using that impact of the hammer could damage it. So bend it over using a sleeve if you're in cool temperatures. But generally, both methods are accepted. And then it's just a matter of did the process of bending that stud over break the stud off or fail the weld in some way? If it didn't, then you're good. You can bend the stud back or leave it. Sometimes the engineer will say you can just leave it bent over. That's okay as long as they've approved it. You don't have to heat it for bending it back up. Threaded studs are a little different for hopefully what are obvious reasons. You don't want to damage the threads, so you're going to do a torque test instead of a bend test, where bending that over would damage the threads. Whether it's a headed stud or a threaded stud, if one or both of those studs fail, then you need to adjust your welder settings, do what you need to do, weld two more, test two more, and if you get another failure, set it aside and work with your supervisor to figure out what's going on. So that's all the two studs at the start. Any change in any of those variables, whether it's the thickness of the plate, the diameter of the stud, the length of the stud, any of that, requires that you treat that like you're restarting. So you got to do two more. Then for continuous stud welding, so say you started up at 7 o'clock and you did your two studs and you kept welding and kept welding. Every hour you need to test two more studs, basically to make sure that nothing has changed with the setup. If you get a failure when you test those two studs, you need to go back and test the previous 10. If any of those fail, go back and test the previous 10 before that until you find a group of 10 without a failure. And you need to check and then either grind the studs off and re-weld them using a different method or repair them some other way, adjust your settings, and then you can continue. When the temperature is below 32 degrees Fahrenheit, one additional stud for every 100 shall be tested to an angle of 15 degrees. So that's sort of nuanced. Just to step back and make sure we understand what's required here. You're testing two studs at the startup, visually, doing a bend test to 30 degrees at startup. You're doing the same thing every hour. If it's really cold, so below 32 degrees, you got to test one additional stud, and this is a quantity trigger versus a time trigger. So one additional stud for every 100 studs needs to be tested to an angle of 15 degrees. And the point of that is just to make double sure that we're not getting any embrittlement of the materials because of the temperature. Similar to welding rebar, no welding below zero or when you're in wet conditions, if it's raining or something. Anytime you've got studs that are being stud welded into the crook or the crotch of an angle. So specifically what we're talking about, if you had like a piece of angle iron and you were welding studs into the reentrant corner of that angle, that's a pretty common condition for like a coping piece or something like that. 100% of those studs have to be tested. And the reason is it's just more difficult to get a good plunge, to get everything oriented correctly. So we're making sure we're testing all of those. And you should strike those with a hammer to make sure that they don't break off. So let's talk really quickly then about doing this visual inspection of the flash. So there's 6 different possibilities that you might see here. So I don't like that they've shown graphically a very thin piece of base material. This actually wouldn't even be allowed, but ignore the thickness of the base metal just for the sake of these diagrams. The first one, you see what's shown here, this is A. So this is a satisfactory stud weld with a good flash formation. And I realize we're not looking at something that can show us all the way around, but we're going to pretend like we can see all the way around. And you can see how this is relatively even. You've got the evidence that you've had a good uniform plunge all the way through. B, this is a stud weld in which the plunge is too short, so you didn't push it down enough maybe, and so you're not seeing that flash all the way around. C is something got hung up in the gun that didn't allow you to plunge that stud down at all. So you can see where it tried to sort of meld together, but it didn't really do it because it didn't plunge down into the steel. And I'll encourage you to look at this. So they've actually drawn these to some type of a scale. So if you were to draw a straight line across here, you can see how this stud is a little bit shorter than this one, and it's quite a bit shorter than C. And that's just showing you that when you push that down into the material, there is a little bit of a length reduction, which is expected. D, this is poor alignment. You can see how that one sort of kicked off so that it's not perfectly plumb. E, this one, you didn't have enough heat. There just wasn't enough heat to melt the two pieces of steel together. And then F, maybe this is one where you can see how much shorter that one is than the rest. There's barely any of that smooth shank left, and the flash is so much wider than the rest just because there was so much molten steel. If you see any of these, B through F, you want to repair it by simply going in and just welding it as if it were a piece of steel. So just do a repair it with a fillet weld all the way around with an electrode, and then bend it and check it, make sure it doesn't break, and then if the weld holds, then it's good. There are some records that are required to document this testing, so I always go out to the weld shop and I ask for a few different things. I'm asking for their personnel qualifications, I'm asking for weld procedure specifications, and I'm making sure those WPSs that are given to me match the types of welds that I'm seeing on embed plates. I am looking at embed plates, I'm looking at welds on embed plates, I am measuring those plates, and then I'm asking for drawings to compare to make sure dimensionally they're all okay, the right rebar, the right studs were used, so on and so forth. But I'm also asking for what we will commonly call just where's your stud bend test log. And so what I'm expecting to see, especially at a plant or only at plants that are using stud guns, and it's easy to find out whether or not they are. You can find an embed plate, and if it looks like it was shot with a gun, then with a stud gun, then you should be asking for this, or you should be keeping this. And it's just a record. It's a document that shows on August 17th at 7 o'clock, we started production operations, and we tested two studs, and they either passed or failed. We did a bend test, and it checked, and the length reduction was 1/8 of an inch. And I'll ask, I'm kind of having to depend on the fab shop to be forthcoming with me, and they'll say, well, yeah, we're usually welding those for 2 or 3 hours, and so I would expect to see subsequent tests on the hour that show that you're doing those tests every hour of continuous production. And so that's basically it for stud welding. We talked a little bit about some other welding concepts as well. But as I said, we cover some of this in level 1 and 2, so this was mostly review and then just adding on to what we learned from level 2. That's it for the day, unless there are any questions that have come in.
We had one question come in so far. He
Okay.
wrote, what is the purpose of the pointed end of the stud?
So the purpose of that little point is just so the stud gun has like a little shoe on it, and that shoe is what helps you orient the gun in a theoretically perfectly upright position. It's a wider, flat surface. If the tip of the stud were flat, it would be kind of harder. It would be maybe deceiving to think that, okay, it kind of feels like I've got it vertical. The point is just a single point of contact, but it also facilitates that arc reaction. The idea is that you get a small contact and then you lift it up, and then that arc is created right there in the middle of that stud, so that that reaction is concentrated right in the middle of where the stud is contacting the plate. So it kind of serves a few different purposes. The main one has to do with that arc reaction. It's concentrating that current right in the middle of the diameter of the stud. Any other questions before we close up shop for the day?
That is the only one that has come in.
Okay, well, I appreciate your attention. I will turn it back over to Lauren.
All right, guys. I'm like giving everybody a second to type as I switch this over just in case. All right. Thank you for attending this session. Certificates of Continuing Education have appeared on your account at www.rcep.net. I have already submitted those. Remember that continuing education credit is given for each individual session. If you have any questions, please let me know. Otherwise, thank you for attending and have a great evening.